Hi, so this lecture is on strain. In class the other day, we looked at some rocks like this one that are highly strained. So if you um, look at all the different sides of this as I kind of rotate it, you see long. They're all kind of elongate. All the crystals. This used to be a granite, um, and when I turn it on the end, though, you can see they're kind of more equine. So granites don't tend to look like this. They look like this when they've been severely deformed. Um, and just as an example of what happened to this rock, so I've got some silly putty here. Um, I'll just draw a circle on it. Okay, and you can imagine a granite is made of a lot of little grains that are sort of semicircular initially, and then uh, this happened to it. Okay, the rock got stretched, and you can see what happened to that circle. That's just the same thing as happened to this rock here. Um, any particular grain that we might look at, has become smeared out, long, much longer and skinnier than it used to be. And so when we go and look at metamorphic rocks, particularly um, especially rocks around New York City, so like the Manhattan schist, for example, we see evidence that they have experienced large amounts of strain. And so the first lecture or two and first lab, we'll be looking in detail at the tools we have, the most basic tools we have to describe the strain mathematically, how we can sort of understand the strain in 3 dimensions. And the goal here is description, basically, just to try to um, you know have some ways that we can communicate what rocks have experienced in terms of their deformation. And so there's going to be a bunch of terms, uh, all different sorts of strain that we'll be describing. And then we can use these. This is how structural geologists communicate with each other. I found a rock that's has a stretch value of 10, for example. Um, and so we're going to learn the basic tools so that we can understand what that would mean. And when we find a rock, when we find a cool rock like this, we can sort of get some sense of what it experienced. Deformation is the sum of two types of motion. These are rigid body motion. So words that we have for this: translation. If we just pick up a glass and move it across the table, translation. Uh, and rotation, we rotate it. So these don't actually involve any distortion of the material. So that falls under the category of deformation. And then the other type of deformation of motion is distortion. So this involves change in shape and or volume. And we define this as, this is what we call strain. We use the epsilon symbol. So strain is a synonym of distortion. And so an example, just north of New York City, we have a situation. So here's kind of the Earth's surface. So like here's a tree, and there's a fault. So things up above the fault are moving in this direction, shown by the little arrow here. Below the fault, we have some layered metamorphosed sedimentary rocks. Above the fault, we have some complexly folded and highly metamorphosed material. So let's say complexly folded metamorphic rocks. And underneath, these are Cambrian, it says just an aged Cambrian metasediments. And this structure here, this is a fault. So we have sort of both examples here. We have these Cambrian metasediments don't show any evidence of distortion. They have been rotated, because most sediments start out as horizontal layers. They're no longer horizontal, they're tilted. So below the fault, we see evidence of rigid body motion. And above, we see these complex folds. These suggest, as we talked about in the first class, most geologic features start out fairly planar or sort of fairly equine or roundish. So these folds suggest that there's been a change in the shape of this material. So deformation is often heterogeneous like this, where we've got sort of different types and scales of deformation. Certainly, like right along the fault, there must be an enormous deformation in order to bring this material from much hotter and deeper levels where this kind of folding can happen, right up next to rocks that weren't very highly buried or deformed. So to simplify this sort of situation, what we'll often do is we'll zoom in on just a small area, a little bit of this that is approximately sort of experiencing all the same sort of deformation. So we're going to limit our discussion to homogeneous strain. Limit to, so we're going to define this thing called homogeneous strain. So in homogeneous strain, straight lines stay straight, parallel lines remain parallel, and circles become ellipses. So this is a very broad category of strain that encompasses many other types of strain that we'll talk about in more detail. So, let's say we start out with some material. It's got like a grid on it. This is the initial condition. And in homogeneous strain, one example would be to sort of squash it and shear it. Those lines that I just drew that are horizontal, they're still parallel to each other. The lines, these other set of lines are still parallel to each other. The lines are still straight. So this would be homogeneous. This would be an example of homogeneous strain. So alternatively, something that if we turn the thing, kind of crumple it up, those lines that were initially straight are no longer straight. They're no longer parallel. This is inhomogeneous strain. So the reason that so this homogeneous strain is much more tractable mathematically. We can describe things that occur, even though nature often gives us inhomogeneous situations. We can describe them or have some hope of describing them by using this approximation of small regions that are essentially homogeneous. So we'll break down homogeneous strain itself. Homogeneous strain is the sum of, let's see, get a little more space. Homogeneous strain is the sum of, first we'll just make it like 0.0 because we're not going to really talk about it too much, but volumetric strain. I'm going to start using the abbreviation for strain, epsilon. So this requires, so this is like the actual volume of the material changes, which we don't see a lot of times with rocks. So this requires a change in density, or some material flux. So some, in the case of rocks, what can often happen is like a fluid will be flowing through the pores of the rocks, and it can either carry away some elements or introduce additional ones. So that can happen. So that, and it would be a, oops, I forgot an S here, homogeneous strain. So basically this volumetric, take a box like that, turn it into that. So the straight lines which make up the top and bottom, or the sides, stay straight and parallel. This is volumetric strain. We also can measure elongation. So this is the shortening and lengthening of lines. So if we have a line of an initial length, we'll call it length sub I. And we stretch this thing so it is a final length. We can define value S called stretch as the ratio of these two, so the final length over the initial length. So if we have a line that is stretched to be twice the its initial length, that would be a stretch of 2. If it's gone the other way from it's originally an inch long and it ends up half an inch long, that'd be a stretch of 0.5. So 50% of it's 50% what it originally was. And we have another related term, elongation itself. So I find stretch to be the most sort of intuitive value, but we have another one, elongation E, which is defined as, let's see, that's the defined as symbol, the length final minus the length initial over the length initial. So this is also equal to the stretch minus 1. So you'll also see, we'll try to focus on stretch, but elongation is also something that we that we'll encounter, for example, in the lab, the first lab. So an elongation that is greater than 0 means the thing got longer. If it's less than 0, it got shorter. So the other component of homogeneous strain is shear. So if we start with initial material and it has kind of a weak plane, and we can transform that into something like this. Okay, so this is the final state. This could be, this is the kind of deformation that would be real easy for a card deck. And we kind of quantify this by defining the shear plane and the perpendicular to it, and that if we were to draw that dashed line on here, we can measure an angle psi. We could also kind of imagine a perpendicular line here. That's also psi. So gamma is equal to the tangent of that angle psi. We call gamma the shear strain. So the shear strain is, so basically, just to think about that for a second. So we have an angle psi. Tangent is the opposite over the adjacent angles. Just to remember. So shear strain is the ratio of like how far we've traveled, a point has moved from here to here compared to how tall it is. So how far we moved, over per vertical distance. So it's, pause for a second and just kind of play around with, what is a shear strain of, a shear strain of 1, would be, look something like that, so where this distance is equal to the height of the box. Shear strain of 2, would have moved a point here, would move this distance and then that distance again to about there maybe. And then remember that all three types here, the shear strain, the elongation, these are examples of homogeneous strain. So in this example as well, the parallel lines that are making up the sides of this box are still parallel. They're just at a different angle, and they're still straight. So these are two of the major criteria for homogeneous strain. And we can combine. We could do both shearing and elongation. And the two are actually, are interrelated in some ways as well. A line, certain lines that we could draw here, like the side of the box, as we shear it, it actually elongates as well. So it's a little bit more complicated than we're presenting it here, but this is a sort of simple way to just get started with homogeneous strain.